Remind you about, it seems to be some confusion, that when you're doing a scan, you first want to set up the scan. It's a whole lot like what you want to do with the iterators that you had when we were doing application programming, where you've got set up your iterator and do, fetch, or next. Same thing there. Setting up your iterator is just setting up to be able to get the tuples that you have inside the scan, and it's doing the next operation that allows you to be able to get the particular tuples. You're not supposed to store all the results inside memory. You're supposed to be getting results one at a time, the way that thing ends up operating. You know about Project 1, which of course has been posted, and you've been using that. Many of you for your assignments. You've seen the notes about forwarding addresses that are there. What I also want to emphasize, and again, I may post a fast note reminding you about that, is that you are supposed to do everything that's in the report. In other words, the report asks you for information about how you've done some things with respect to scans and forwarding addresses and so on. Please be sure that the things that the report asks you to do is stuff that you actually do in the report. Your grading is going to end up being based on that. You know about the public tests or private tests. You also know about the 2 extra credit parts of this. The adding an attribute extra credit is actually stuff we've talked about in class, so that's not too bad. The thing about dropping an attribute or deleting an attribute is a little bit harder. And then next Monday we have the midterm, and you know the drill from 180. No makeups, earlies, or lates, no devices. You get to bring in the so-called cheat sheet, which we'll be collecting. You do have to show your ID when the exam is over. We not only now have the midterm from last year, but also the answers to that exam were posted yesterday. So you should be able to see the answers to the exam as well. Let me know if you have questions. As usual, I'm not going to be devoting Friday to a review. If you have questions, please post them on Piazza, and I'll see what I can do about answering those questions about the course in general or about what was in the spring 2018 midterm. As I always tell you, I can talk fast, but I can't go over all the material in the term together, and I don't do a review where I say, here's what's on the exam, now write it down on the exam. You're supposed to know what's been discussed in class, so I hope that that all ends up working out. We'll be posting the Project 2 solution on Friday and also Project 3, but you'll be glad to know that you get 3 weeks to do Project 3 because there is this midterm that's in the middle. So you will have 3 weeks to be able to do it. And again, you can do Project 3, which is a B-tree project. You can do Project 3, which I'll talk more about after the midterm. But you can do it either based on our Project 2 solution or based on your own. Okay, now also a question that's been asked that may answer your question right now. This lecture, Lecture 9, will be on the midterm, but although we will be starting Lecture 10 either today or more likely on Friday, Lecture 10 will not be on the midterm. So this is Lecture 9, continuing talking about join. It will be on the midterm, but Lecture 10 will not be. Did I answer your question?
Well, that was one of them. The other one was, will the extra credit also be included in the solution?
I don't think that we post an extra credit solution, but I can talk to you. I can post something explaining how the extra credit can be done. The extra credit for the ad, I've already gone over how you do it in class. That was something that we discussed. There are a bunch of different approaches to doing the one where you drop the attribute, and if there's interest, and it seems to be, I'll talk about at least one way that you could deal with that if you wanted. I'm happy to talk about it if there was interest, but the solution doesn't include it. It doesn't include either one. Okay. So, because you don't need them for the later assignments.
Oh, okay.
Okay. So we're across Lecture 9 and Lecture 10. We'll be talking about how you end up executing a bunch of different operations. And we've been talking a lot about join, but in Lecture 10, we'll be talking about the other operations as well. Again, Lecture 9 will be on the midterm, Lecture 10, the next one won't be. So this lecture is. And of course, this is an important part of figuring out execution plans. You have to have ways of being able to execute each operation. The wonderful thing about SQL is that not only are things composable when you write queries, but also the operations that are there are things that can be composed to be able to create an execution plan that handles a subpart of the query and compose that together with something with another operation that allows you to get an execution plan for a bigger subpart of the query. And that's the general idea of how we're going to be doing things. So we'll be looking at execution, then we'll be looking as we go up from the bottom of the way a system works, and then we'll be looking about optimization, which says, well, making some assumptions about what the costs are and what the statistics are, how do we find a pretty good way of executing the entire query using information that's in the catalog. So we're on join. Reminder again, because we'll be using these numbers throughout, reserves has basically 100,000 reservations. Could have called it reservations, but that's longer to say. So there are 100,000 reservations, 100 tuples per page, 1,000 pages, each tuple 40 bytes long. In sailors, there are 40,000 sailing club members, and there are 500 pages with 80 tuples per page, and each tuple is 50 bytes long. And so that's the notation we're using. And the only reason I remind you about this one, which is, I hope, pretty easy to remember, is it is different from the books. And the books, I can't defend the books. I like this a lot better, so I use it. Pages from R, pages from reserve. And we've already talked about, the approach to join. And we went over both the simple nested loop join and the page-oriented nested loop join. The difference with the two being that you're going to be joining everything on a pair of pages. Instead of for every tuple, find every matching tuple. By looping through all of S, it's for every page, take a look at every page of the second relation S and do all the matches between the pairs of pages, and that ends up being a lot cheaper. We've talked about the index nested loop join, but I'll remind you about that because I also want to talk to you about what the costing is for that. So the way that nested loop join is, we're going to loop through basically every page of R. We only have to touch each page of R once, and then for every tuple that's on a given page of R, what are we going to do? We're going to find all the tuples in S. We're not going to go through the pages of S. The assumption is there's an index on the join column of S. The join column of S is S of J, the join column of R is R sub I. And since we have a tuple from R in our hands, have our hands around its neck, one by one person, right? You go ahead and, since you have R sub I, you can look up all the S sub J's using the index on S sub J. You can find all the tuples in S that have that same value for the join column. You have a particular fixed value of R sub I, so you can look up using the index where are the S tuples whose S sub J column matches R sub I. And you can get those using the index. And for every one that does, you add the R tuple, S tuple, or whatever columns of it you need into your result. And that's a join algorithm using indexes, so that's kind of cool. So the way that it would work is you're going to go through every page in R, look at all the tuples on that page and find the matching tuples inside inside S. So you're going to go through the pages of R, that's the pages of R part. And then for every tuple of R, that's the cardinality of R part, you're going to have to get the matching S tuples. What's the cost of that? Probing S, if you have a hash index, it's going to be a cost of about 1.2. It's going to be between 2 and 4 of if you have a B tree. And then, assuming that we're using alternative 2 or 3, it's not just probing the index, you also have to get the tuples. And the cost of getting the tuples, if you have a clustering index, that could be about 1 IO to get the tuple. And if you have an unclustered index, then it's going to be probably 1 IO per matching tuple that you have. And typically, again, situations might be unclustered. The nice thing about our situation with sailors is we know that there can only be one matching sailor for a reservation, because there can only be one sailor with a given SID. So we're actually going to look at that example and see how that works in practice. So suppose that we have a hash index, alternative 2, on the SID column of sailors. So here's what we're gonna do. Reserves is gonna be the outer, that's gonna be R in this example. We'll look at the alternative in a second. But we're gonna have a hash index and SID. We're looking through all the reserve pages and then looking at all the tuples on that page. Okay, so there are 1,000 pages inside reserves. I went over that again, 1,000 pages in reserves, 100 tuples per page, that's 100K tuples. Okay, so then for each reserve tuples, it's gonna be something where you need to be able to get the corresponding sailor. So it's gonna be 1.2 IOs to get the data entry for the corresponding sailor. I probably should add a word emphasizing. We're gonna have to get the matching sailor. So we have our hands around the neck of a reserve tuple. You wanna get the corresponding sailor. 1.2 IOs to be able to use the hash index if things aren't in memory. And then there's exactly one, or zero if we don't have referential integrity. There's exactly one sailor tuple. You've got an SID. SID is the key of sailors. You want to get the SID in reserves, find the matching SID inside sailors. Normally you'll have referential integrity. You can't have a reserve tuple for a sailor that doesn't exist. But it'll be one matching sailor's tuple. So there's one IO to be able to get that, assuming things aren't in memory. The stupid assumption that we're making, because making more realistic assumptions, I mean, there are two reasonable assumptions to make unless you really want to have complicated formulas. Assumption number one, nothing's in memory, that's what we're doing here, it's silly. Assumption number two, which is more realistic today, which is that just about everything is inside memory, because people really do try to keep nearly everything inside memory where possible. But if you have really large relations, you may actually have to get the data. There are good formulas for figuring out, and the book goes into them, for figuring out what you should assume, typical costs would be, if you have a given number of pages and things are uniformly in memory and not memory, but we're not gonna go into the detail. So the cost of doing this is gonna be the 1,000 IOs to scan reserves. And now, to get the sailor that corresponds to that SID inside reserves, it's gonna be 1.2 things using the hash index to get basically the RID for the sailor tuple, and one IO to get the sailor tuple, because there can be only one. So it's gonna be 1,000 plus 100,000 times 1.2 plus 1, 100,000 times 2.2, that's where the 220,000 comes from. And you put that together with 1,000 IOs, and that's gonna be the cost of executing that plan. Now, something I wanna emphasize, this is worthwhile understanding, even though today it's thoroughly bogus, because you want to understand how the calculations are done for figuring it out. The calculations you would do today, first of all, it's not in our textbook. Typically, you don't have textbooks that really go into the detail of what you would really work with today, except by saying, well, just assume everything's in memory. So you might go to the opposite assumption. Instead of assuming nothing's in memory, they assume everything's in memory. In which case, there are interesting CPU costs to be able to go into. And that really is worthwhile, again, especially if you're thinking about the NUMA issues of how all this stuff works. But just understanding how the calculations are done, even though it's bogus, and I emphasize that it is still worthwhile. So now we're gonna go ahead, before we had reserves as outer and sailors as inner. Now we're gonna go the other way. We're gonna go ahead and we're gonna have sailors as outer using the nested loop join, and we're gonna have reserves as inner. And the assumption, again, is that there is a hash index on the join column of the inner relation, reserves. As I mentioned last time, sometimes if there isn't an index, you might create one. It's costly, but it might make the whole thing run faster than if you hadn't created the index, even though you have to pay the price of creating the index. So, you're gonna go through every page of sailors, and then for every tuple on sailors, you're gonna find the matching reserves. This is the way the index nested loop join goes, where you're gonna use the index to find the matching reserves. So then, for each one of your sailors tuples, it's gonna be 1.2 IOs to use the index to find the thing that allows you to actually find basically the RID for the matching reserves data. But there may be multiple reserves for an individual sailor. So for an individual reserves, there can only be one sailor who has that reservation. But for an individual seller, that seller could have a whole bunch of different reservations. If you assume uniform distribution, since there are 100,000, which by the way is an unreasonable assumption, right? The reasonable assumptions make this much more complicated. So we're making an unreasonable assumption that distribution is uniform. There are 100,000 reservations, there are 40,000 sellers, so on average, a seller has 2.5 reservations. How the seller got the half reservation, I'm not gonna justify. But there are 2.5 on average reservations per seller, okay? And so for each seller, you're gonna have, it's gonna be 1.2 IOs to be able to find the RIDs in the hash table of the the SIDs in the hash table of the corresponding reservation, right? So to get the tuples. So basically, you're gonna have to go ahead and get the corresponding tuples, and the cost of getting those reservations is gonna be, on average, either 2.5, 1 IO per tuple, if it's not a clustered index, right? And if it is a clustered index, then those tuples are probably gonna be on the same page, so it's only gonna be 1 IO. So again, they're gonna be on average 2.5 tuples that you need. If you have a clustered index on SID, and it might be something where, with a B tree, it's gonna be something where if it's a clustered B tree, you'll find them typically on the same page, and if it's not clustered, you'll find them on different pages. Then we talked about something called the block nested loop join, and this uses a hash table, but it's not the same as a hash join. We will get to hash join today. Hash join is really pleasant, but you can get an idea of what's going to come up in hash join through what we discussed in nested loop join. We discussed this already, but now we're going to do the costing. So the difference between this lecture and the previous one is we talked about a bunch of stuff without going over the cost. This lecture actually gives the cost. So recall the idea. We're going to go ahead and we're going to bring in as many blocks as we can from R. In this thing where there are no shadows for the extra pages, we're going to have one input buffer for S. And we'll have one input buffer for the outputs. Again, this is stupid, as what we did with the external merge sort. It's good to be able to have these shadow blocks so you don't have to wait for an IO to happen. But again, it makes the description of this more complicated, but in practice, it really is what you want to do. So you have one block where you're just going to put in a block. You're going to go through all the blocks in S, one at a time. And you have one block where you have the output. And when an output block fills up, you're going to write out the output, so you'll have an empty output block and so on. Again, in practice, you would want to have more than one, but we're just going to show how this works in the case of one. Easy to generalize to have 2 instead of 1. Well, if you have a total of B buffers, then what you're going to do is you're going to have a value of K which is less than B minus 1. Let's say K is B minus 2. That's a good value that's less than B minus 1. So we're going to have B minus 2 blocks that we're going to use for a hash table. And what we're going to do is we're going to bring in B minus 2 blocks of R. The first B minus 2 blocks of R. We're going to put them into the hash table. Now the hash table actually, this is cheating a little bit because the hash table takes a little more space than the raw blocks of R. So it really will have to be, you won't be able to bring in a full B minus 2 blocks of R. Maybe you'll bring in B minus 3 or some other overhead Y, because the hash table has a little bit of overhead in it. So B minus 2 records is going to take more than B minus 2 blocks for representation. So maybe it's B minus 3 or B minus 4, but we're not going to focus on the overhead involved, although in practice you really do. So I'm going to be simple now. I bring in the first B minus 2 blocks of R, put them in a hash table, which again, naively, I'm assuming fits in B minus 2 buffers in that way. And now what I'm going to do is I'm going to go through all the tuples in that block of S. And I don't have to scan the B minus 2 blocks of R. I've put them in a hash table. So this is not saying that I have a hash index on R. I'm reading in the data from R, just doing a file scan, but reading in B minus 2 blocks, which will be fast if they're sequential, so that I can do next to be able to read them in. In fact, I can just get them consecutively by doing a request out to the device to bring in B minus 2 blocks. Again, things change a bit with SSD, but here with this, the sequential matter. And now, how am I going to find the matching tuples in R for a tuple that I have from S, I take my first tuple of S. I use the same hash function that I used to construct the hash table on R, on the B minus 2 blocks of R. And I find my matches. And I take the next tuple of my block of S, and I find all the matches. And I do this for every tuple that I have inside this single buffer that I have for S. And every time I find a match, I put things in my output buffer. The RS tuples go in the output buffer. When I'm done with my one buffer for S, I go on to the next buffer for S, and the next buffer for S. And for that same hash table with the first B minus 2 blocks that I have of R, I'll do this for every block of S and every tuple inside that block. And when I'm done, I've matched up that B minus 2 blocks of R with all of S. But I'm not done yet, because there might be more than B minus 2 blocks inside R. That's fine. I've dealt with a group of B minus 2 blocks that I have inside R. I'll now bring in the next B minus 2 blocks of R. And I'll put them into a hash table the same way, using the same hash function. And I'll do the same deal where block by block I go through this and I put out the outputs. And so this is a nested loop join, but it's done with a group of blocks. The name block nested loop join is in some ways a terrible name. It's taking a group of things and putting it in a hash table. So it's sort of halfway between a nested loop join and the hash join we're going to get to soon. So everybody got the idea? You take B minus 2 blocks at a time of R, you put them in the hash table, which really takes a little more than B minus 2 blocks. And you go through blocks of S one by one. And you don't have to search the B minus 2 blocks because you put them in using the hash function. That's a little overhead, constructing the hashed version of it. But then it's very easy to find the matches inside those B minus 2 blocks of R for every single S tuple that you have in that block, and then for all the subsequent blocks of S. Questions about this? Yeah.
So the only I/O is the loading of the blocks into the hash table.
The only I/O is the loading of for R is the loading of the blocks into the hash table. Of course, for S, what you're going to be doing for every B minus 2 blocks, you're going to have to load all of this in. And in fact, we're going to get to that calculation in the next slide. Another question? No. Okay.
Oh.
Yeah.
So when there's a match in for the hash table from S to like the hash table to blocks of R,
Yep.
that goes into the output buffer.
Yep. As usual, anytime you have a match on the join column, that goes, or some subset of the pairs of columns go into your output buffer. And again, you have the ugliness over here that when the output buffer is full, you have to take the time to write it out. In practice, you wouldn't have just one input buffer and one output buffer. You might have 2 or more, that we're dealing with. I'm just not showing that. We showed it with the external work sort, but the same trick applies here.
Okay, thank you.
Okay, so numbers. That's the difference in this lecture. We're talking numbers. So basically, the cost of doing the block nested loop join is you go ahead and you have your outer table, by which I mean R. And then what you're going to do is you're going to have, for every B minus 2, so this is another reuse of the term block. I don't like the term block. I like the book for so many things, but the word block is, I like puns, but this is a bad pun. You have a B minus 2 block, B minus 2 page group. So basically, you're going to have to go through R. Remember, you read the first B minus 2 blocks of R. Then you read the next B minus 2 blocks of R. So you only have to touch each block of R exactly once per your question, right? Even though you're doing it in B minus 2, block groups. And then take the number of groups that you have, which is basically, pages of R divided by B minus 2. Right? How many groups do you have? How many times do you have to build the hash table? You take the size of R, the number of pages of R, divided by B minus 2. So that's what that number of outer blocks is. Yuck. It's a number of groups. But that's the term in the book. And then you have to go through the inner. Remember, we have to get S a block at a time. So for each group that I had of R blocks, I'm going to have to scan S through. So I don't have to do it for every block of R. I only have to do it for each group of blocks of R. So that's what's going on there. Okay? So the number of these outer blocks, the number of groups, is the number of pages in the outer table divided by the again, block size is confusing, basically divided by b minus 2, the number of things that I'm reading together. So again, the terminology stinks. I didn't try to revise this one since it's a one-time use, but you got the idea. It's these groups that you're dealing with. So basically, if you have reserves as the outer, and you have 100-page size groups of R, your hash table has 100 pages inside it, then basically the cost of scanning R is going to be 1,000, so that's the outer, that's going to be 1,000. And there will be 10 groups, right? There will be 10 groups. Again, I hate the term blocks for this. There will be 10 groups total that you end up having. And so the number of times that you end up scanning sailors is going to be 10 times because there are 10 groups. Sailors has 500 blocks and 500 pages in it. Block pages, confusing, but again, there are going to be 10 groups. Sailors has 500 pages in it, so for S, you're going to have 5,000 IOs. So the total cost of this is going to be 1,000 plus 5,000, which is 6,000. Okay, so you end up having to touch each page of R once, that's 1,000, and then because you have 10 groups, each of which is 100 pages, you're going to be touching all of S, 500 pages, once for each of these reserve groups. So that's going to be a total of 1,000 plus 5,000. Question on that? Again, the terminology stinks. Question?
Why do we use exact numbers like this instead of big O notation like in other algorithms?
The reason that we're using exact numbers is that that's what the optimizer uses to try to figure this out, and we want to see which way thing is better. So in some cases we want to see what the numbers look like, even though the numbers are just approximate and ugly. I mean, it's one thing to be able to say that, you remember when you're using, big O or, omega or theta or whatever notation, you're saying, well, the order matters when n is big enough.
Yeah.
I care about what happens when n is big, small, or somewhere in between. The numbers matters. Constants matter. I mean, I've taught 101, I'll be teaching 201 next fall. Ignore constants at your peril. Okay, I mean, they matter, especially in stuff like this. Okay, so now we're going to do the same thing, but now we're going to have sailors as being the outer. So basically, there are 500. You're going to have every page inside sailors touch once. You're going to form groups of things from sailors, but each page of sailors gets touched once as we bring in b minus 2 things of sailors. So basically, the cost of scanning sailors is going to be 500 IOs. If we assume that our b minus 2 is 100, so that means that we're going to have 5 groups, not blocks, 5 groups of b minus 2 things. Okay, so then per S block, you're going to have to scan reserves how many times? 5, because they're going to be 5 of these groups, not blocks. There are 5 groups. For each group, you have to scan all of reserves. The reserves has 1,000 pages inside it, so that's going to be a cost of 5,000. So basically, what you're going to do is get 5,000 plus 100. This is going to be 5,100 versus the 6,000 that we got for the other. Okay. So basically, there are other variations of this that you may want to play with the trade-off of how many things you give to R and how many things you give to S. There are various ways that you can trade this off that are more sophisticated that we're not going to go into. Okay, we also talked about sort merge, and again, the difference in this lecture is we're talking about the algorithms again. I'll remind you about them, but we're doing a sort merge where we're looking at R sub I equals S sub J. And the way that sort merge operates, remember how the thing works. It's another use of the term traffic cop, having nothing to do with my use of the word traffic cop in B trees. But basically what you're going to do is you're going to sort R on its join column, or join columns, by the way. Sometimes you join on multiple columns. You're going to sort R on its join column. You're going to sort S on its join column. So it's going to be the time to be able to do the sort. And now you're going to go do the merge by saying, whichever one is smaller, I'll advance until I've got a tie. When I've got a tie, for each R tuple, I'm gonna find all the matching things in S. And now the next R tuple that has the same value, all the matching things in S. And the next R tuple, all the matching things in S. Until I get to a point where there are no cross matches for the current value. So, if for 79 I find 8 things here and 12 things here, there'll be 96 things that come out because they also all have join column equal to 79. But again, remember, for a given tuple there may be no matches, there may be a whole bunch of different matches. Again, I can have 12 things in R matching 8 things in S, that produces 96 tuples in the answer. So you keep advancing again until you get a tie. When you get a tie, you take all ties between all the different pairs. And this will find all the matching values of Ri and Sj as you end up going through, and you output R and S or whatever subset of the columns you want to deal with. Remember, you don't have to output all of the attributes if you don't want to. You only care about the ones that are relevant for what you're doing later. It's not what have you done for me lately, it's what are you going to do for me next. No reason to keep around irrelevant attributes, just as there's no reason to keep around non-irrelevant rows. Okay, so that's the way that algorithm ends up working. So basically, R is scanned once, okay, and then when you find a match for each R tuple, you're gonna have to scan the group of S tuples that match it, all right? And then if there's another R tuple that has the exact same value, you'll scan the same group of S tuples that match it. They all have the value 79. So there'll be a bunch of R tuples that have value 79. All the S tuples that have value 79 are going to have to be scanned again and again and again for each R tuple that matches, so you can put them out. But the assumption is that if you have touched, even with something naive like an LRU algorithm, if you have just touched a group of tuples that have matching values, then they're going to be in memory. And maybe you're smarter than that, and the database is doing its own buffer management and saying, I'm not going to get rid of these pages until I know that I can get past because I've switched to a new value of R, or moving off the page. So, example. Okay, so you end up having a bunch of sailors, you end up having a bunch of reservations. The left-hand thing is the sailors table, the right-hand thing is a reserves or reservations table, okay? And basically, if you have, remember we went over external sort. If you have X pages, so X is the number of pages here, the cost of sorting X pages where it may not fit inside memory is going to be, where B is the number of pages, the buffer pages you have, is going to be 2 times the number of pages, 2x, times 1 plus the ceiling of log to the base b minus 1 of ceiling of x over b. That one is for the first pass. Okay, so that's going to be the way things work. Notice again, it's log to the base b minus 1. Because we needed a page for the output buffer. Okay, so that was what the cost was when we did the external sort. So the cost of doing a sort merge is going to be the cost to sort the pages of R, all of R, plus the cost of sorting the pages of S, all of S. Okay, plus, and now where is that pages of R plus pages of S coming from? To do a sort merge, you sort R, you sort S, and you merge them together. You only touch each tuple of R once, each page of R once, as you go through the pages inside the result. Notice that it's the sorted R that you're touching now. And now, why is it for S that it's also just pages of S? Well, if we're making the assumption that when we have a group of tied values, that the S tuples will still be in the buffer. Because remember, we're not touching the original S, we're touching the sorted S as we're going ahead and doing the merge. So the number of pages in the sorted S is the number of pages, same as the number of pages in the unsorted S. So you touch each of those pages once, because even when you have to go back and say, oh, here's here's an R tuple that matches these 1,000 tuples that have the value 79. Now here's another R tuple that matches them. Those 1,000 tuples in the pages that we're in will still end up being in memory. So even though you may have to go back a little bit, because there can be multiple ties with value 79, the things are going to be in memory, so each page of S gets touched once. So it's going to be plus pages of R. Okay? Now, there is an exception case. I've already mentioned it. Skew is trouble. Skew is trouble no matter what. But it really is trouble if everything in the join column matches everything else in the join column. Doesn't happen very often, but it can. Because remember, if everything matches everything, then you're gonna have to match everything to everything. So if there are M pages in R and N pages in S, or if you want pages of R, pages of S, the result is gonna be, the total number of pages in the result is gonna be pages of R times pages of S, because everything matches everything. In general, that doesn't happen. In general, it doesn't happen. So, again, as an example, if you had 35 or 100 or 300 buffer pages, that is, if B is 35 or 100 or 300, then, you know, the reserves and sellers can both be sorted in 2 passes. That's gonna be the thing where you end up having the ceiling, the log to the B minus 1 of ceiling of X divided by B. It's gonna be 2. The calculations are not very hard. If you have trouble figuring out what that is, take a look back at our sort lecture. But it's gonna be 2 passes. So basically, it's gonna end up being something where you end up getting a join cost, which is gonna be the cost to sort reserves, which is gonna be this 2 times 1,000 pages in R times 2, because it's 2 passes. So that's gonna be the 1 plus ceiling, etc. It's just gonna be 2. Plus the same thing with respect to sellers. And then the adding together the pages of R and the pages of S. So that's gonna come up to 4,000, right? Plus 2,000, plus 1,000, plus 500, which is 7,500. So that's gonna be the cost of using that algorithm in that case. As a reminder, the blacklisted loop join, if we did that, which we just went over with that, you know, funny, you know, B minus 2 things inside a hash table, could depend on what the number of value of B is, and it'll be between 2,500 and 15,000. So notice that in some cases BNL is better, blacklisted loop join is better, because 2,500 is better than 7,500. On the other hand, 15,000 is worse, so it really does depend on how many buffer pages you have, if you're looking at the cost of the sum. And now we come to what is a really, really pretty algorithm. Hope you've enjoyed the algorithms for sorting, for joining so far, but this is one that I think you may enjoy even more, and that I hope you're prepared for. And this is referred to as the Grace hash join algorithm. And there are a number of other variations of hash join that are described in the text that we're not going to go into. We're going to talk about the main one, which is Grace hash join. And it's got 2 phases in it. And the first phase is called the build phase. And the second phase, which we're going to get to, is called the match phase. And in the build phase, what you're going to do is you're going to build hashes. But not just for one of the relations. You're going to use the exact same hash function, which, with my usual lack of imagination, we're going to call H. You're going to use the exact same hash function on both R and on S. Okay? So I will use my hash function. I'll have a given number of values. Let's say there are B minus 1 different values that I will use, which here are listed as 1 through B minus 1. If you wanted to call them 0 through B minus 2, you could, but that doesn't matter. It's the same deal. So you're going to build something where there are going to be B minus 1 values of your hash function. And you're going to hash R, and you're going to hash S. And what